All right, let's talk about the single most important material you've probably never really thought about, semiconductors. They are the invisible silent brains running pretty much everything in our modern world, from the phone in your hand to the satellites circling the globe. So let's dig in and see how they actually work.
And it really all comes down to this one kind of wild question. How does something as ordinary as silicon, the main ingredient in sand, become the engine of our entire digital universe? How on earth does a simple rock learn to think? Well, to figure that out, we first have to solve a pretty fundamental problem with electricity.
So that challenge, it brings us right to our first big idea, the hunt for a Goldilocks material. See, the goal wasn't just about getting electricity to flow. It was about controlling that flow with absolute pinpoint precision.
So think about it like this. On one hand, you've got stuff like copper. They're conductors. Electricity just zips right through them, no problem. They're basically always on. Then, on the other extreme, you've got insulators, like rubber or glass. They stop electricity cold. They're always off. But what if you need something in between? Something that isn't just stuck on or off, but can actually choose.
And that, my friends, is where our hero comes in, the semiconductor. Just like the name says, its ability to conduct is somewhere in the middle. It's not always on, it's not always off. It is the just right material. And it turns out substances like silicon are absolutely perfect for the job.
But here's the twist. In its pure, natural state, silicon is, it's actually a terrible conductor. When it's cold and pure, its electrons are all locked up tight, so it basically acts like one of those off materials, an insulator. Its true power is locked away, and to make it useful, we have to find the key.
And that's exactly what we're going to do in this next part. We are going to teach this humble little rock some seriously incredible new tricks through a process that basically gives it electrical superpowers. Okay, so the secret sauce here is a process called doping. Picture this. You start with this perfect, pristine crystal of pure silicon. Then you deliberately mix in a tiny, tiny bit of something else, an impurity like arsenic. Now, arsenic has one more electron in its outer shell than silicon does. So when it slots into that silicon crystal, that extra electron has nowhere to go. It's just hanging around. It becomes a free electron that can zip around and carry a current.
So this whole doping thing, it gives us two different flavors of silicon. The one we just made with those extra free electrons we call N-type, for negative. But you can do the opposite too. You can dope silicon with an element that has one fewer electron. This creates the absence of an electron, which we call a hole. And this hole acts just like a positive charge, so we call this P-type silicon, for positive. So now we've got two brand new materials, one with mobile negative charges and one with mobile positive charges. So, we've got these two new materials. A natural question, right? What happens if we stick them together? Well, as we're about to see, we can build our very first fundamental electronic component, a one-way gate for electricity.
The moment you press a piece of P-type silicon against an N-type piece, you create what's called a PN junction. And right at that border, something really cool happens. The free electrons from the N side immediately rush over to fill in the holes on the P side. This creates this thin little zone right in the middle. We call it the depletion layer, which has no free charges left. It becomes a barrier, stopping any more electricity from flowing.
But here's the magic. We can control that barrier. If we apply a voltage in just the right way, we call it forward bias, we can literally push the electrons and holes towards the barrier, squishing it until current can flow. Boom! The gate swings open. It's on. But if we flip that voltage around, that's reverse bias, we pull the charges away from the barrier, making it wider and stronger. No current can get through. The gate is off. What we've made is a perfect one-way street for electricity.
Okay, so a one-way street for electricity. Big deal, right? Well, it is a huge deal because it does this critical job called rectification. See, the power coming out of your wall socket is alternating current, AC. It's constantly flipping back and forth. But all of our gadgets, our phones, our laptops, they need direct current, DC, a steady one-way flow. This simple little PN junction, this diode, acts like a filter, letting the current through in only one direction, turning that messy AC into the stable DC power that runs our digital lives.
Okay, we've built a one-way gate. That's cool. But now we're going to take it to the next level. We're going to see how combining these junctions leads us to, maybe the single most important invention of the 20th century.
Say hello to the transistor. If a diode is a simple PN junction,
A transistor is what you get when you make a little semiconductor sandwich, like an NPN configuration. This clever setup gives you two PN junctions, back to back, and it lets us do something that is truly magical. Use a tiny, tiny electrical signal to control a much, much bigger one.
You know, the best way to think about it is like a water faucet. You've got your emitter, that's the main water pipe, the source of all the charge. You've got your collector, that's the spout where the water comes out. And then you have the base, that thin little layer in the middle, that's the faucet handle.
And this is the whole shebang, the crucial point. A tiny, tiny twist of that handle, a super small electrical current sent to the base, can control a massive flow of current from the emitter to the collector. This ability to either amplify a small signal or to switch a huge current on and off with a tiny one is the absolute foundation of every single electronic device you own.
What this gives us is a perfect switch, an absolutely perfect switch. It has no moving parts, so it never wears out. It can flick on and off billions of times a second. And most importantly, those two states, on and off, that's it. That's the physical reality behind the ones and zeros of binary code. This humble little switch is the language of all computers, and it's what makes everything possible, from a basic calculator to a supercomputer to a satellite. And the scale here is just mind-bending. It's estimated that there are about 100 quadrillion transistors on Earth right now. I mean, that's a number so big it's hard to even wrap your head around it. We manufacture them by the billions on a single tiny chip, each one a perfect little switch that started out as a simple rock. So when you really think about it, these transistors aren't just little components. They are the literal atoms of our digital reality. Every email you send, every photo you take, every single bit of information flying across the internet is being processed by these microscopic silicon switches. And that leaves us with one last big question. Now that we've used them to build this world, what are we going to build with them next?